weapon is controversial. North Korea claims to have tested a fusion weapon as of January 2016, though this claim is disputed. Thermonuclear weapons are considered much more difficult to successfully design and execute than primitive fission weapons. Almost all of the nuclear weapons deployed today use the thermonuclear design because it results in an explosion hundreds of times stronger than that of a fission bomb of similar weight. Thermonuclear bombs work by using the energy of a fission bomb to compress and heat fusion fuel. In the Teller-Ulam design, which accounts for all multi-megaton yield hydrogen bombs, this is accomplished by placing a fission bomb and fusion fuel, tritium, deuterium, or lithium deuteride, in proximity within a special radiation-reflecting container. When the fission bomb is detonated, gamma rays and X-rays emitted first compress the fusion fuel, then heat it to thermonuclear temperatures. The ensuing fusion reaction creates enormous numbers of high-speed neutrons, which can then induce fission in materials not normally prone to it, such as depleted uranium. Each of these components is known as a stage, with the fission bomb as the primary and the fusion capsule as the secondary. In large, megaton-range hydrogen bombs, about half of the yield comes from the final fissioning of depleted uranium. Virtually all thermonuclear weapons deployed today use the two-stage design described to the right, but it is possible to add additional fusion stages, each stage igniting a larger amount of fusion fuel in the next stage. This technique can be used to construct thermonuclear weapons of arbitrarily large yield. This is in contrast to fission bombs, which are limited in their explosive power due to criticality danger, premature nuclear chain reaction caused by too large amounts of pre-assembled fissile fuel. The largest nuclear weapon ever detonated, the Tsar Bomba of the USSR, which released an energy equivalent of over 50 megatons of TNT, 200 mpj, was a three-stage weapon. Most thermonuclear weapons are considerably smaller than this, due to practical constraints from missile warhead space and weight requirements. In the early 1950s, the Livermore Laboratory in the United States had plans for the testing of two massive bombs, Gnomon and Sundial, 1 gigaton of TNT and 10 gigatons of TNT, respectively. Fusion reactions do not create fission products, and thus contribute far less to the creation of nuclear fallout than fission reactions. But because all thermonuclear weapons contain at least one fission stage, and many high-yield thermonuclear devices have a final fission stage, thermonuclear weapons can generate at least as much nuclear fallout as fission-only weapons. Furthermore, high-yield thermonuclear explosions, most dangerously ground bursts, have the force to lift radioactive debris upwards past the tropopause into the stratosphere, where the calm, non-turbulent winds permit the debris to travel great distances from the burst, eventually settling and unpredictably contaminating areas far removed from the target of the explosion. There are other types of nuclear weapons as well. For example, a boosted fission weapon is a fission bomb that increases its explosive yield through a small number of fusion reactions, but it is not a fusion bomb. In the boosted bomb, the neutrons produced by the fusion reactions serve primarily to increase the efficiency of the fission bomb. There are two types of boosted fission bomb, internally boosted, in which a deuterium-tritium mixture is injected into the bomb core, and externally boosted, in which concentric shells of lithium deuteride and depleted uranium are layered on the outside of the fission bomb core. The external method of boosting enabled the USSR to field the first partially thermonuclear weapons, but it is now obsolete because it demands a spherical bomb geometry, which was adequate during the 1950s arms race, when bomber aircraft were the only available delivery vehicles. The detonation of any nuclear weapon is accompanied by a blast of neutron radiation. Surrounding a nuclear weapon with suitable materials, such as cobalt or gold, creates a weapon known as a salted bomb. This device can produce exceptionally large quantities of long-lived radioactive contamination. It has been conjectured that such a device could serve as a doomsday weapon, because such a large quantity of radioactivities with half-lives of decades lifted into the stratosphere where winds would distribute it around the globe would make all life on the planet extinct. In connection with the Strategic Defense Initiative, research into the nuclear pump laser was conducted under the DoD program Project Excalibur, but this did not result in a working weapon. The concept involves the tapping of the energy of an exploding nuclear bomb to power a single-shot laser that is directed at a distant target. During the Starfish Prime high-altitude nuclear test in 1962, an unexpected effect was produced, which is called a nuclear electromagnetic pulse. This is an intense flash of electromagnetic energy produced by a rain of high-energy electrons, which in turn are produced by a nuclear bomb's gamma rays. This flash of energy can permanently destroy or disrupt electronic equipment if insufficiently shielded. It has been proposed to use this effect to disable an enemy's military and civilian infrastructure as an adjunct to other nuclear or conventional military operations. By itself, it could as well be useful to terrorists for crippling a nation's economic electronics-based infrastructure. Because the effect is most effectively produced by high-altitude nuclear detonations, by military weapons delivered by air, though ground bursts also produce EMP effects over a localized area, it can produce damage to electronics over a wide, even continental, geographical area. Research has been done into the possibility of pure fusion bombs, nuclear weapons that consist of fusion reactions without requiring a fission bomb to initiate them. Such a device might provide a simpler path to thermonuclear weapons than one that required the development of fission weapons first, and pure fusion weapons would create significantly less nuclear fallout than other thermonuclear weapons because they would not disperse fission products. In 1998, the United States Department of Energy divulged that the United States had made a substantial investment in the past